So we're going to look at the concept of this, what we call a solid of revolution. All right, and what we're doing is we're taking the area underneath a curve and we're spinning it around the x-axis. Okay, we're spinning it around. So you see here, we have an area under a curve like this. And then we take it and we revolve it 2 pi or 360 degrees around the x-axis. Okay? And we end up with this solid object. Okay? Now the video that we just looked at actually has it, with a hole inside of it. And we'll do those in the next lesson. But you say, okay, well, how in the world would we find the volume of this? It actually all goes back to the cylinder, okay? Let me actually look at the volume of a cylinder. The volume of a cylinder is the area of the base times the height. And since it's a cylinder, the base is pi r squared, okay? So we have pi r squared h. Okay, that's the volume of the cylinder. Well, let's look at this. If we were going to go from A to B, okay, and let's say that we just had a constant function. Let's say the function was the line y equals, not h, r. Okay? So here is whatever r is. All right, so we've got this horizontal line. Okay? And what we end up doing is we take this rectangle and we spin it around the x-axis, and that actually gives us the cylinder that we're looking for. Okay? So here is where it would be down below, okay? Here's our cylinder. And I can make the bottom solid because you'd actually see that. Okay? So there's our cylinder with the x-axis going straight through the middle of it. All right? Now, because we used the line y equals r, the r is going to be the radius, okay? But you guys know from geometry that the height is how far apart the two bases are, okay? Well, what is the height in this case? It's a b minus a. B minus a. So the volume of this object is actually going to be pi r squared times b minus a. Okay? Now, you guys know that r is a constant in this example. Okay? And we learned before that the integral of a constant is just the constant times b minus a. Okay? The constant times x of b minus a. So if you think about this, we could say that this is the integral of pi times r dr. Sorry, not dr, dx from a to b. Okay?
Wait, can you start again? Sorry.
It's the integral of pi r squared. Sorry, the r should be squared. Okay? From a to b.
Okay.
So what you're doing here is you're taking this circle, this base, pi r squared, and you are adding up the infinitely thin disks that make up this cylinder, and that's where you get the b minus a for the height. Okay? Now, let's suppose that r was not a constant. Okay? Let me draw another xy axis down here. And let's say we had some function that looked like this. Okay? And again, I'm going to go from A to B. But you'll notice that the shape I'm going to come up with is going to be very different than just a cylinder. Okay? You know, here it's going to go down this far. Here it's going to go down this far. At B it's going to go down a little bit further. Okay? And we can get approximately what this is going to be. Something that looks kind of like this. Alright, so if we revolved this green thing around the x-axis, we would get something that kind of looked like this. Almost like an hourglass shape. Okay? Now, I want to use the same concept here, except I want you to notice here that the radius is not going to be constant. What is the radius going to equal?
The y value.
The y value. Whatever the y coordinate is there, that's what the radius is going to be. So let's call that f of x. Okay? This whole thing is f of x, but that r, depending on where we're at, is going to be f of x. Okay? So for example here, over here at A, the radius would equal f of a. Over here at B, the radius would be f of b. Okay? So, what we're going to do is use the same concept. We're going to use that pi r squared, recognizing that r is changing. So the area of the base here is pi f of x squared. But we need to do pi r squared times the height. Well, how do we do times the height? The same way we did it up here. We're going to take the integral from a to b of this. Okay? And that's how we can find the volume of this thing getting spun around the x-axis. And in fact, we have a little bit of a refined formula given to us. And this is also in your formula booklet this way. But we could write this as pi times the integral from a to b of y squared dx. Okay? This is, and actually in your formula booklet, it actually even leaves the pi inside. Pi y squared dx. Why doesn't it matter where the pi is? Yeah, pi is a constant. Okay, so it doesn't matter if it's inside or outside. I like leaving it outside because then you don't have to mess with it till the very end. Do the whole integral and just multiply it by pi at the end. Okay? So that's the idea. That's the idea of what we're doing here. We're given a function, we're going to spin it around the x-axis, so we do pi times the integral from a to b of the function squared dx. Okay? So let's look at an example that we could do geometrically. And I actually want to do it geometrically first. Okay? Using geometry, what's the volume of a cone?
1/3 pi r squared, like pi r squared.
Very good. It's a cylinder times 1/3. Okay? So it's the volume of a cone is 1/3 pi r squared h. Okay? So let's go ahead and look at this one closely here. This is the line y equals x going from 1 to 4. So up here, that's the point 4, 4. So the radius of this large cone is 4. This right here is at 1, so the point is 1, 1. So the radius there equals 1. Okay, now I need both of those because notice here my cone has the top cut off. So I need the entire cone, which is going to be 1/3 pi times the radius squared times the height, so 4 squared times the height of 4. But then I have to subtract the little tip. The tip is a 1/3 pi, r is 1 squared, times the height, which is 1. Okay? So, I have 1/3 pi times 16 minus 1, if you think about it. Or 1/3 pi times 16 minus 1/3 pi. So now there's only...
What happened to the other 4?
Oh wait, yeah, thank you. Not 16, 64. Oh. Hate it when it does that. 64. Okay?
And what did you say it was, so it was tip minus something, I'm sorry, can you repeat what you said?
The whole thing has a radius of 4 and a height of 4.
Mm-hmm.
The tip that's cut off there, close to the origin, has a radius of 1 and a height of 1.
Thank you.
Okay? So 1/3 pi times 64 minus 1/3 pi times 1 is 1/3 pi times 63. So now I'll do the 1/3 times the 63, and I get 21 pi as my volume. Okay? Now that's using the geometry. Yes.
Do you want us to leave it in terms of pi? Or
Yeah.
If it's 1/3 pi times 64 minus 1/3 pi, wouldn't that just be 64 because the two pi's?
Times 1, so then you combine like terms.
If you factor out the 1/3 pi, you have a 64 minus a 1.
Okay.
Yeah. Now let's do this again using the formula, and I think you'll see how this does kind of simplify things for us a bit. I'd say, wait, so calculus simplifies things for us. It does, okay? Because here, the volume is going to be pi times the integral from 1 to 4 of the function. The function is y equals x. dx. So now it's a matter of simple integration. We've got pi times x cubed over 3 dx, or not dx, evaluated from 1 to 4. Okay, so that's pi times 4 cubed over 3 is 64 thirds. Minus 1 cubed over 3 is 1/3. And there you have 63 thirds,
Times 5.
which is 21 pi.
I like that way a lot better. Yeah.
It does make it simpler, okay? And not only that, not only in a situation where we can use geometry does it actually make it simpler, but we also have obviously an infinite number of possibilities where you can't do it with geometry, okay? There's no way to, there are things that there just aren't formulas for, okay? So we're able to do those now as well. But here you can see it does work for ones that we could have done with geometry, okay? So let's do one more here where we do not, or we cannot use geometry to find it. Here we have the function y equals x squared. So we have our parent function of the parabola, okay, from 0 to 5. So we're taking this region right here, and we are going to spin this around the x-axis, okay? So it's going to look like this big cone kind of thing. Comes to a point. Maybe it's like a birthday hat or something. I don't know. Okay? But here we have that. So again, we just use our formula. It's pi times the integral from a to b. What's a to b?
0 to 5.
0 to 5 of the function squared dx. So the function is already an x squared, so we're integrating x to the 4th. Pi times the integral from 0 to 5 of x to the 4th dx. Okay? So now we're back to just the simple integrals that we've done in the past. Evaluate this from 0 to 5, which is kind of cool because when you plug in 0, it's 0. So it's pi times 5 to the 5th over 5
Wait,
is 5 to the 4th. And 5 to the 4th is 625.
why do you have x to the 4th power?
Because it's, the formula is the integral from a to b of y squared.
Oh, okay. And the y is
Already squared, so it's going to be.
Yeah, the y is already squared, so it's squared squared, so it's to the 4th power. Okay? So yeah, so our volume here is 625 pi cubic units, whatever our units happen to be.
I don't want to get too ahead, but like, what if instead of saying revolve through 2 pi, it said through pi, or through like something smaller than 360?
Okay, that's a good question. This is revolved through 2 pi. If we wanted to, what if we wanted to revolve it through, oh, let's pick a interesting one.
Well, if it's just
Pi over
pi,
2.
you can just divide by 2, right?
Yeah. Or let's say it's one of our other, let's say it's
90 degrees.
7 pi over 4.
It's 90 degrees, just divide by 4.
Yeah, okay. But the same principle there, the proportional size still applies. If we wanted to revolve it through the angle 7 pi over 4, I could set up a proportion or a ratio here. I don't want the full 2 pi. I want 7 pi over 4 out of 2 pi. Okay? So what fraction is that? Well, the pi's will cancel, and that's actually 7/8. Okay? That's 7/8 of a full rotation or a revolution. So that means my volume would be 7/8 of the total volume. So I would just take 7/8 times 625 pi, and whatever that gave me is what my answer would be. It would 375 pi.
This one's revolved through 2 pi though.
This one is, yeah, he was just saying what if.
Oh, okay.
Okay? And I will say for your sakes, I've never actually seen one on an IB exam where they didn't do it through a full 2 pi or a full 360. But it's cool to look at. I mean, we could make it just a partial design it that way too. So, good thought. All right. So that's it for that part. I'm going to give you guys some time to practice with a few of these. You'll realize that basically every problem is identical, okay? So let's take some time here to practice with them. And then in our next lesson, we'll look at what if we want to cut a hole in it and make it hollow.
Huh?
Huh?
Because why not, right?
Why not? Yeah.
Or